Ever wondered how AI models process information so efficiently? Today, we're diving deep into the mechanics of transformer architectures, the backbone of modern language models. If you've ever wondered how systems like GPT or BERT achieve such remarkable performance, this video is for you. Before transformers, recurrent neural networks (RNNs) and their variants like LSTMs dominated sequence modeling. But these architectures faced critical challenges: vanishing gradients, sequential processing bottlenecks, and limited parallelization. Imagine trying to process a 1,000-word document one word at a time. Inefficient, right? That's where transformers revolutionized the field. Transformers replace recurrence with self-attention mechanisms. Let's break this down. At their core, transformers use three key components: query, key, and value vectors. For every word in a sequence, the model generates these vectors and computes attention scores by comparing the query of one word to the keys of all others. This allows the model to weigh the importance of different words dynamically. Here's where it gets interesting. The attention score is calculated using the dot product of the query and key vectors, scaled by the square root of the key dimension. This scaled score is then passed through a softmax function to produce weights. These weights are multiplied by the value vectors, and the results are summed to produce the final output. This process happens in parallel across all words, enabling massive efficiency gains. But wait, how does the model understand word order? Enter positional encoding. Unlike RNNs, which process sequences step by step, transformers need an explicit way to encode position. This is achieved through sine and cosine functions of different frequencies, added to word embeddings. The result? A mathematical representation of position that allows the model to infer relationships between words regardless of their distance. Once attention mechanisms have processed the sequence, the data flows through feed-forward networks, simple neural networks with a hidden layer. These networks apply nonlinear transformations to the attention outputs. To stabilize training, transformers use layer normalization, which standardizes the inputs across the batch and feature dimensions. This is critical for handling the deep architectures typical of modern models. The impact of transformers is everywhere. From machine translation to code generation, their ability to capture long-range dependencies and scale efficiently has redefined what's possible. But there's a trade-off. The computational cost of self-attention grows quadratically with sequence length. Researchers are actively addressing this with innovations like sparse attention and linearization techniques. So what's the takeaway? Transformers aren't just another model. They're a paradigm shift in how we approach sequence modeling. By prioritizing parallelization and dynamic attention, they've unlocked new frontiers in AI. If you're curious about the math behind attention mechanisms or want to explore implementations, check the description for resources. Thanks for watching, stay curious, and keep pushing the boundaries of what's possible. Like this video. Subscribe for more deep dives into AI research. Until next time, keep learning.